Okay, let's continue for the chapter 2. So the remaining of chapter 2 are section 2.5, Gauss's law, section 2.6, the law of conservation of charge, and section 2.7, application to static fields. So the remaining two Maxwell equations are pertinent to the surface integral of the electric and magnetic field over closed surfaces. And they are referred to as Gauss's laws of electrical field and magnetic field. For the electrical field, the Gauss's law for electrical field states that displacement flux emanating from a closed surface. Displacement flux 也就是我们看到那个 D 啦哈 ，emanating 是穿出去的啊，所以朝外朝你的那个封闭面穿出去的。Displacement flux emanating from a closed surface S is equal to the charge containing within the volume V bounded by the surfaces. So the implication of these statements can be illustrated with this figure. So as long as you have a bunch of electrical charge, which can be in the form of point charge, surface charge, or volume charge, as long as you have a region of electrical charge and you draw a surface that enclosing this region. So now that this should be the so-called closed surface, 一个完整的封闭面。Then the displacement flux or electric flux D, the total electrical flux D emanating out of this closed surface. The surface integration, the closed surface integration of D should equals to the amount of electrical charge enclosed in this region. So the direct implication of this statement is that, electrical charge produce electrical field. So as long as you can find out a non-zero electrical field or electrical flux enclosing a specific region, then you can determine that there are electrical charges reside within this volume, reside within this space. So in the mathematical form, it's written as equation 2.25. So to the left is integral. A surface integral, 一个面积分 a closed surface integral, 一个封闭的面积分 So as you can see here, it's not only a surface integral of displacement flux D, it's also a closed surface integral. So since this is a closed surface, then the region, the space within this closed surface is a volume. Then to the right is the charge, the total charge reside within this volume, reside within this space. So the right-hand side of equation 2.25 can be replaced with another integral that is a volume integral. 这是一个体积分了所以注意一下，在这个高斯电场定律的左右边，左边是一个电通量密度的封闭面积分，右边是电荷密度的体积分So the total charge can be calculated as a volume integral of electrical charge within this volume, within this space. So it's written as the volume integral of rho, that is the electrical charge density. It's a volume integral over the region V. And so therefore the volume integral is a triple integral since dV is the product of three differential lengths. And one thing that I need to remind you is the line integral is a vector. The line integral, the differential length itself is a vector, dl. dl is a vector. The surface integral, ds, is vector as well. However, the product of the volume integral dv is a scalar. It's a scalar. So be careful about the property of it as a scalar or a vector. And because dv is the so-called scalar triple product, so the outcome is a scalar, not a vector. All right, so we see the official form of Gauss's law for the electrical field is the closed surface integral of displacement flux d equals to the volume integral of electrical charge low within that space. And d, the electrical flux density or displacement flux density referred in the test, can be written as epsilon E, as it is the more general form. And here is epsilon sub 0. What is the significance of the subscript 0? It refers to that epsilon sub 0 is the permittivity for vacuum, for vacuum or for empty space. This is referred to as the permittivity, as I already mentioned a couple of times. And other relationship pertinent to this form is B equals to mu H and J equals to sigma E. These three are referred to as the constitutive relationship. Which will be discussed again in chapter 4.1 to 4.3 for those three relationship, because they determines the material's electromagnetic property. 所以材料的电磁特性其实就这三个关系来描述。所以材料的电磁特性简单讲就是它的 epsilon mu 跟 sigma。假如它 sigma 重要的话，那个东西叫做导体 conductor。If sigma is relatively large, and it is usually referred as the conductor, such as metal. If the material's permeability介磁系数 permeability is particularly important, then it's referred to as magnetic material, like magnet 磁铁了哈 magnetic material。有比较更正式的名词了哈，叫做 ferromagnetic material 哈。不过好了，以后我们再讲好了。And if this material does not have a significant value in conductivity and permeability, then they are referred to as dielectric. 介电材料所以一般你看到的大部分的材料，它只要没有明显的导电性或者磁性的话，那就叫做介电材料dielectric material. Alright? 所以我们提前把那个第4章的 4.1 到 4.3 上完了其实就这样而已OK 我们还回到 2.5 了So let's go back to our discussion about Gauss's law. And so to the left is the closed surface integral of displacement flux density d, which equals to epsilon sub 0 times E if the space is a vacuum. And to the right is the volume integral of electrical charge density low. So it's formulated in terms of volume charge density. Volume charge density. However, it can be replaced with surface integral of surface charge density or line integral of line charge density. But anyway, it's to the right is a calculation of the total charge within that space. So this is essentially the Gauss's law for the electrical field. Next, let's look at the fourth equation, that is the Gauss's law for the magnetic field, which is relatively simple because first it's analogous to the Gauss's law of electrical field. So to the left is also a closed surface integral of flux density. That is the closed surface integral of magnetic flux density B. And to the right is 0. Well, you may be curious why the right-hand side is 0. Can it be a non-zero value? Well, theoretically speaking, it can be a non-zero value. Unfortunately, so for all the experiment or all the observation made so far, we do not see any proof or any experiment result that we have a non-zero value on the right-hand side. 所以这个视觉右边在理论上它其实是可以不是零的哈，因为理论上假如你有幸或者是不幸研究所的时候要上我的高等电磁学的话，那个我们在高等电磁学的那个 Maxwell equation 其实这个的右边其实写作这个的，它不是零啊，它一样是一个 volume integral， 跟那个高斯电场定律一样不是写错，跟高斯电场定律一样，它的右边都是一个 volume integral。只是说这个我们写作1好了所以代表还是 low 是电荷密度，所以 low m 是什么？磁荷密度其实它们是对称的其实它们是对称的，但是没有人看过磁荷啦，没有人看过磁荷，所以等于0。大概在15年前有一次我在上那个电磁学之前看到一个英国报道说某人发现了磁荷的存在。那发现的过程是因为他在那个厕所蹲了太久了，站起来的时候看到一堆星星火花之类的，不是还类似反正他说他看到了磁荷啦他有做实验证明出磁荷然后那个其他人就讲说，哇，那太好，我们电磁学可以丢掉，不要写了或者我们电磁学要重新写过一遍了那当然那种英国报道就不要太相信它了OK 到后来我们其实还是没有证明所谓的磁荷存在了。虽然在我们在高等电磁学里头，我们有等效的磁荷或者是磁流就像真实的那个讯号源有电荷、电流。然后，其实我们也有发明所谓的磁荷，还有磁流 ，low m 跟 m 这是磁流不过还好，在我们的基础电磁学里头，你不用去担心这些事情所以高斯磁场定律的右边就等于0那为什么等于0？当然，简单的讲法就是我们没有磁荷 ，no stand-alone magnetic charge。那更直观或者更从实验来看的一个做法，来看的一个讲法就是 ，because the magnetic field always form a loop, as you can see from a magnet. If you have a magnet over here, of course you can draw the magnetic field distribution of the region. And if you define a region in the neighborhood of the magnet, and if the region is enclosed by a closed surface, then if you do the calculation of the magnetic field or the magnetic flux emanating， 注意哦 ，emanating 指的是穿出去的哦，所以假如它是真的穿出去，那这个是正值；那假如穿进来嘞，那它就是负值了啊。So if you calculate the closed surface integral of magnetic field or magnetic flux density within this closed surface, then it always equals to 0. Why? Because the magnetic field lines will form a loop. So it will goes into the space and goes out of the space for every magnetic field line. So as long as they are always form a loop, or there is no standalone magnetic charge, then the closed surface integral of magnetic field or magnetic flux density equals to 0 at all times. All right? So this is simply a fact that you can claim that because there is no standalone magnetic charge, or there is the magnetic field always form a closed loop, then both conditions will end up with 0 for the magnetic field closed surface integral of the magnetic field. All right. So to put it another way is because magnetic charge do not exist, and magnetic flux lines are closed at all times. So the closed surface integral of magnetic flux density always equals to 0. No matter how you twist or tweak the surface. So here's a more interesting surface that it has an outer bound and an inner bound as well. But as you can see here, because the magnetic field forms loops at all times, it goes into the region and goes out of the region. Anyway, so the net magnetic flux goes into and out of the region always equals to 0. All right, and the other property associated with the closed surface integral for Gauss's law is we can use the property that magnetic field is the computation of magnetic flux crossing a given surface can be replaced with another surface that has the same bound, have the same boundary, have the same contour. For example, S1 is a triangular surface bounded by these 3 lines on this Cartesian coordinate axis. However, S1, which is bounded by this triangle, can be replaced with surface integral of S2 plus S3 and S4. We know that S2 and S3 and S4 are surfaces that are different to S1. However, if you combine S2, S3, and S4 together, their boundary, their contour is the same as S1. Then the calculation for the collection of magnetic flux passing through S1 must equal to the magnetic flux passing through S2, S3, and S4. So this is a useful property that you can replace because the magnetic flux is, for a closed surface, is always 0. So you can replace surface integral with regions or surfaces that are easier to calculate. And here is another example for the relationship of Gauss's law of magnetic field with respect to the Faraday's law. As we know, or as we have perceived for this course, we introduce 4 equations for the so-called Maxwell equation. We have 4 equations, okay? If you ask me, my preference is I think the Maxwell equation is actually 4 plus 1, 5 equations, which the 5th equation is the so-called continuity equation that will be introduced in section 2.6, which will be introduced, which we will see pretty quickly. However, some physicists claim that, Maxwell equation can be written in just 1 equation. It's true. It's true. You can you probably can reduce the number of Maxwell equations into 1, because in fact, the 4 Maxwell equations, or 4 plus 1, the 5 Maxwell equations are related to each other. They are not independent. They are coupled to each other. As we have already seen that Faraday's law and Ampere's Kirchhoff law are coupled. 也就是法拉第定律跟那个安培电路定律，也就是磁生电、电生磁，它们其实是不独立的它们其实是互相关系的那同样的，高斯电场定律还有高斯磁场定律也分别跟法拉第定律还有安培电路定律有关所以这4条关系是并不是互相独立的，而是都有关系的那所以物理学家要说Maxwell equation 只有1条也是可以的，但是假如你把它写成1条，那就不好用不好用。所以从工程的观点，从处理问题的观点来讲，然后现在我们所看到的 Maxwell equation 4+1条其实是好用的。因为老实讲啦，你只要回到150年，当 Maxwell 刚推论出他的 Maxwell equation 的时候，他其实有20条的。20条，然后那个时候拆得更细碎那当然经过这个推导啦合并之后整理出来现在的形式。因为现在我们所看到 Maxwell equation 的形式，其实不是 Maxwell 整理的，是我们现在看到的形式，其实是 Maxwell 的学生赫兹，还有另外一位科学家叫 Heaviside 他们2个所整理出来的。只是那个后来爱因斯坦在讲说这个19世纪和20世纪，19世纪最重大的发现就是 Maxwell equation 所以所有的功劳又通通变到 Maxwell 身上去了但其实你现在看到的这些这个 Maxwell equation 的形式，其实也不是当初 Maxwell 所给出来的Alright, so go back to the slide. We can see that in view of the foregoing discussion, it can be seen that Gauss's law for the magnetic field is not independent of Faraday's law. So here we can try to associate the 4th Maxwell equation with the 1st Maxwell equation. As you can see here, if you have an egg-like volume, egg-like space, then you cut the eggshell in half. Then to the left is surface S1, which is bounded by C1, and to the right is surface S2 and bounded by contour C2. So as you can see here, C1 and C2 are in fact the same contour with their orientation, their direction are opposite to each other. And the collection of S1 surface and S2 surface forms what? Forms a closed surface. So we can write the Faraday's law for the left side and the right side of the eggshell. So to the left side, we see the closed loop integral of E on C1, contour C1 equals to the minus of the time derivative of B, the closed surface, the surface integral of B over S1 region. And you can write a similar equation for the left-hand side. So they refers to the electrical motive force accumulated on the contour equals to the negative of the time derivative of magnetic flux passing through the two associated space. Then if you add up the two equations, because C1 and C2 are literally the same contour with opposite direction, the left-hand side adds up as 0, while the right-hand side becomes the negative of time derivative of a closed surface integral of magnetic flux B over S1 plus S2. Can we get the result of this directly? Well, no. because that equation involves time derivative. So to get rid of the time derivative, you need to do a time integration. And it's supposed to be a constant to the other side of the equal mark. However, based on experimental evidence that we have never seen a closed or a standalone magnetic charge. So the right-hand side, which is a constant, which is the result of the time domain integration, which is constant, because we haven't seen any evidence of it, so we use 0.所以这个不是一个很严格的数学上面的证明或推论，但是从实验的证据来看的话，从工程的角度来看，因为至少到目前为止，它看起来还是0，但哪一天你只要脑袋被苹果敲到，或许你能够找到证明有独立磁合的办法，那我们的电磁学就可以为你而重新再改写了OK。So, because the time derivative of magnetic flux passing through a closed surface equals to 0, so the integration of that thing is a constant value, and because we didn't observe any standalone magnetic charge, so the value can be chosen as 0 for the meantime, all right? So this concludes section 2.5. So let me take a few minutes to discuss a little bit about section 2.6. This is referred to as conservation of charge. And this is the so-called fifth Maxwell equation from my own opinion, from my own perspective. I think the conservation of charge, which is used for the integral form. In the differential form, this equation is referred to as the continuity equation. And this equation, this relationship provides a bridge to get to bridging the four Maxwell equation. Now, because the existence of this equation, you can easily integrate the four Maxwell equation to be a dependent system, all right? And so the conservation of charge is formally known as the law of conservation of charge. And this can be found by linking the second and third Maxwell equation, that is, the Ampere-Secchio law and the Gauss's law for the electrical field. 在上一页我们看到的是 Maxwell equation 的1跟4，也就是高斯磁场定律跟法拉第定律。这里头呢，我们看到的是，假如你把安培电路定律跟高斯电场定律一起看的时候，看在一起的时候，它就会给你这一个电荷连续定理。好，所以有了这个电荷连续定理，其实你们就可以把所有的那个 Maxwell equation link 在一起 The law of conservation of charge states that the net current due to the flow of charge emanating from a closed surface S is equal to the time rate of decrease of the charge within the volume V bounded by S. So before our description about this equation, let's think about something. Well, it's spring times, and in spring times you will have what? You will have thunderstorm. Why? Because the presence of thunder. What happens before the thunderstorm take place? 雷雨或打雷的现象要发生之前会发生什么事情？你会看到天边飘来一朵云嘛，对不对？好 ，So suppose on a plane, and we have a house, and of course this is a standalone house. So to evade the risk of electrical charge, electrical. To evade the risk of lightning, you have to install. 看避雷针的英文怎么讲？我都忘记了。OK， 好。All right. So what happens if the cloud of the thunderstorm moves in? What happens? Well, on the surface, it seems that there's nothing happens. You only see the clouds moving. But as an electrical engineer, you know that something is going on, right? You have a collection of electrical charge from the cloud, and as the clouds move in, it will attract electrical charge of opposite polarity. So as the time evolves, as the time goes, there will be more and more electrical charge moving into this device. Then what happens? The electrical field intensity between the two objects will build up, which means you will have a so-called displacement current. As we already introduced last week, displacement current. This is not a real charge movement, but the effect of the displacement current is the same as real current. So even though that we didn't see anything happens within this scenario, it can be approximate that there is an electrical current going this way, which forms a closed current loop. And the only thing that, well, this is real current, IC, conduction or combustion current. However, this place is the displacement current. So the current loop is formed as we accumulate more and more electrical charge on the cloud side and on the house side, right? And eventually, what happens? 最后出现什么事？就是要互换皮卡丘啊，对不对？好，当你的那个电场的大小 when the electrical field gets to the threshold. The threshold means that the electrical field is so strong that it can pull out of the electron from the molecule or molecule composition. 可以把电子从气态分子里头直接拔出来的时候，我们就有闪电了嘛，就那个 breakdown 的这个 voltage. Okay, so pretty similar as what we observe in the formulation of a capacitor. The process of the lightning also involves the magnetic flux. So here is another view about this thing. So at the tip of the electrode, at the tip of the electrode, you can have real currents goes in. Then what happens? You will accumulate more and more electrical charge within this space. So, is this what happens? What is not shown in this figure? What is not shown in this figure is that there are actual currents, electric charge moves in, and there are more and more charge built up at the tip of the line. And as I already mentioned, electrical currents must form a loop. Therefore, the electrical currents continuous in terms of displacement currents. Now, because there are more and more Q within this space, so you have a time derivative of D. And this time derivative of D is the displacement current, and that will continue this current loop to the other end, all right? So we can express this relationship of this figure in mathematical form. So to the left is the surface integral of electrical current density. Now that's the surface, that is the actual currents moved in. And to the right is the minus of the time derivative of electrical charge density. That is the Q accumulated in this region. One thing that you should notice is this is positive, this is minus. Positive sign over here, minus sign over here. Because in this drawing, the I is moved in, and the amount of Q is built up. So in fact, for this figure, you should draw a minus sign over here and a positive sign over here. But well, it's still correct. It's still correct. Depending on how you determine the positive current flow direction, all right? So after with the integration, it becomes R equals to the time derivative of Q. Now, so which is not that difficult to understand. For a closed surface, for a region, if the Q is getting more and more, if you have more and more electrical charge as the times pass, then you know that there are some currents moves in. On the other hand, if the Q, total charge within the spaces, becomes smaller and smaller, then you know that there is a current, actual current flowing out of the space. So you have a minus sign over here. All right, so the physical interpretation can be seen in this slide. The net current flow, the net electrical current flow equals to the time rate of electrical charge, of reduced electrical charge within this closed surface. And if this is true, the implication of this thing is there is a current flowing out of the space. So as the electrical charge becomes smaller and smaller within this volume, this means there are currents flowing out of this out of this closed space. All right. Let's see. Okay, now I'll leave that to Thursday, right?